All right, so in the last session, we heard a lot about the IMF, and in particular, we heard Charlie talk about observational constraints on the IMF, and we heard a little bit of the theory from Deshika. I'm going to try and tell you a little bit more about the IMF and understanding where it comes from on a theoretical basis and what that implies about sort of galaxy formation. Now, I apologize. I know that most of you regard the IMF as an utter nuisance. It is not the object of love for you that it is for me. All right. Nonetheless, I'm going to try and explain to you a little bit of the theory behind where does the IMF come from? How do we think about its origin? All right. So I'll start with a crash course in modeling the IMF, and in particular on what I'll call the isothermal conundrum and the two ways around it. All right. Then I'll spend most of my time on the IMF from non-isothermal turbulent fragmentation.
Sorry, you only want one screen.
I'll leave two. Why not?
Okay.
You going to do something fancy?
No, it's just,
We were waiting.
Yeah, as I said, if you can do stereo in your head, it'll be 3D. Yeah, I can go like that, which is what everyone does anyway. All right, and finally, I'll end on implications. All right, so let me start with my crash course on how to think about the IMF. All right, now, if you ask a star formation theorist, like, where does the IMF come from? Why is the typical star, of order the mass of the sun? They'll probably start mumbling something about the gene's mass. And they'll say, well, all right, the characteristic mass of a star is set by the gene's mass in a molecular cloud. All right, and the gene's mass depends on the sound speed and the density. And if you plug in characteristic numbers appropriate for molecular clouds, like a temperature of order 10 Kelvin, density of order 10 to the 5, you get something like half a solar mass, which is sort of reasonable. All right. Any star formation theorist who says this is lying to you. They are bullshitting you. All right, here, let me let you in on a dirty secret. The dirty secret is this argument only works if you know the answer in advance. And the reason is, giant molecular clouds do have roughly constant temperatures. That is a reasonable temperature. But how did I pick that density? Molecular clouds don't have constant densities. Their densities vary hugely. Now, I put in the density of, sort of a dense star-forming clump, and that's reasonable, but I could quite as reasonably have chosen the mean density of a GMC measured on, say, 10 or 50 parsec scales. All right, more like 10 to the 2, and then I get 13 solar masses, and that looks a hell of a lot less impressive. The moral of the story is that this is not a good argument by itself. All right, you only can use this argument if you know the answer in advance. Now, this is actually concealing a deep fact about isothermal gas, and this is what I'll call the isothermal conundrum. All right, I apologize. This is now fluid dynamics land. All right. That's right. That's right, I apologize. But they're up there for sheer intimidation value. No, all right. Here's the physics. All right. Suppose I have an isothermal, magnetized, self-gravitating, turbulent gas cloud, the sort of thing I think a giant molecular cloud is. All right, how many energies are there in the problem I just described? Well, there's the thermal energy, all right. There's the bulk kinetic energy. This thing is supersonically turbulent. There's the magnetic energy. And there's the gravitational energy. So from these four energies in the problem, I can make three-dimensionless ratios. And those three-dimensionless numbers fully characterize the problem. If I tell you those three-dimensionless numbers, you know everything. All right, and those three-dimensionless numbers can be things like the Mach number. That's basically the ratio of bulk kinetic to thermal energy. The plasma beta, that's something like thermal to magnetic energy. The number of genes masses, that's basically thermal over gravitational. The Alfvén Mach number, the mass to flux ratio in units of the critical magnetic mass to flux ratio for aficionados, the turbulent genes number, the virial ratio. The point is, there are only three-dimensionless numbers in this problem. All right, and here's the problem. These dimensionless numbers are invariant under the following scaling, but the mass is not invariant. All right, so this immediately tells you you cannot determine a mass scale from the problem I just described to you. All right, that is a molecular cloud that is turbulent, magnetized, isothermal, self-gravitating, has no characteristic mass scale in it. All right, simply from dimensional analysis, I can prove it has no characteristic mass. Now, the practical implication of this is that if someone does a simulation of an isothermal gas cloud, and they say, look, I did a simulation, this gas cloud fragmented, and look, I got the IMF, the peak is at 0.5 solar masses, it's in exactly the right place. That would be another example of them bullshitting you. All right, because the simulation is totally dimensionless, and they could have rescaled it so that the peak of the IMF wasn't 0.5 solar masses, it was 0.5 Jupiter masses, or say 0.5 times the mass of the entire Milky Way galaxy. And those simulations would have been identical to machine precision to the one they just did. All right, so this immediately tells you you cannot, from isothermal gas, get a characteristic mass scale. So any explanation of the IMF has to involve getting rid of this assumption of isothermality. And every theory of where the IMF comes from is just a different way of doing that. So you have to give up the isothermal assumption to explain a characteristic mass scale. All right, so that's the isothermal conundrum. So how do you do that? And theories of the origin of the IMF can be broken into categories based on how they resolve this dilemma. All right, so here's one approach. You break it from galactic properties. What you say is, well, all right, giant molecular clouds are roughly isothermal, but in fact, they're sitting in a galaxy that is decidedly not isothermal. All right, your giant molecular cloud is sitting in the midst of this galaxy that's full of atomic and ionized gas. That stuff's not isothermal. So what I'm going to do is, somehow, I'm going to look at GMCs on galactic scales, and I'm going to say that those properties on galactic scales are what determine the peak of the IMF. All right, and you can do that either by just saying that there's a characteristic Jeans mass in molecular clouds, and that's what I'm going to take the IMF peak to be. All right, and that's what Narayan, and that's what Desica just talked about. All right, or you can invoke the line width size relation that characterizes turbulent media, and for example, Phil Hopkins has tried to do that. All right, so that's one approach, and I actually think it's not the right way to go, and here's why, for 3 reasons. First of all, if I buy this, well then the characteristic peak mass should depend on the density of the molecular cloud that's forming the stars. Now you can test this very directly in the Milky Way because we've got star-forming regions of wildly different densities. I can go look at Orion. That's 2 orders of magnitude denser in terms of, say, stars per cubic parsec than Taurus. So do the IMFs of those regions peak at different places? Well, no, not in the slightest. They're all the same. You can go to globular clusters. That's orders of magnitude denser than anything in the Milky Way. The IMF peak sits in roughly the same place. I mean, now, you could argue for factor of 2 level variation. All right, but there's like 6 orders of magnitude in density, and that is just not showing up in characteristic mass. So I think that's argument number 1. Argument number 2 is that, well, saying I'm going to get it from the characteristic Jeans mass of the cloud, please identify for me in this picture the cloud. All right, this is an extinction map of a nearby star-forming molecular cloud. All right, the gray scale is just showing extinction. All right, the little dots are showing where the young stellar objects are. Which contour is the cloud? Now, depending on which one you pick, you can get the Jeans mass to vary by at least a factor of 10, probably more than that. Which one are you going to pick? I don't think you can answer that question sensibly. Similarly, there's no single line width size relation that characterizes molecular clouds that you could use. All right, so that doesn't work. Problem 3 is that if you actually try and simulate an isothermal medium, you get the result I just described to you, which is that there is no characteristic mass scale. In fact, if you do isothermal simulations, what you find is the gas always just fragments down to the lowest mass you're capable of resolving. It looks something like this. Here's a simulation by Martel et al., all right, where they're showing that you have this collapsing filament, and this filament fragments, and you notice the very regular spacing of those red dots. Those are the sync particles, the stars. That regular spacing is 1 SPH kernel. That's not an accident, all right? In fact, they did this simulation at a bunch of different resolutions, and these are these 3 different resolutions, and you'll notice the characteristic mass just keeps on moving down as the resolution does. This is actually a well-known result in the star formation community. Physically, what's going on is that for a collapsing isothermal gas, the characteristic solution is not a singular point, it's a singular line. It's a singular filament. All right, if I have isothermal gas, it'll just collapse as a filament to infinite line density. And if you want to break that up into stars, well, either you need to not be isothermal, or your simulation can be non-isothermal for you because it only has so much resolution, and that's the answer you get. So that's why I don't think isothermal fragmentation with the isothermality broken on large scales is a sensible approach. So let me talk about a different approach. The different approach is that you recognize, well, molecular clouds aren't quite isothermal. And why are they not quite isothermal? Well, it's because stars do this thing that we like to forget about as star formation theorists. They shine. And when they shine, they put out light. And that light heats up the gas and dust around them. All right, so here's just a toy calculation I did, more than 5 years ago now, showing the temperature as a function of distance from a forming star. And the red line is the temperature distribution immediately before collapse to stellar density occurs. That is, before there's any heating due to accretion luminosity. That blue line is the temperature as a function of distance at the point when the star has grown to 0.8 solar masses. What you can see is that I've changed the temperature by a factor of 10 out to distances of like 1,000 AU. Now that's not a lot if you think about galaxies. All right, but that's not a trivial fraction of the total distance between stars, the characteristic size of a star-forming region. All right, this is the way you break isothermality. So let's see if we can make a story out of this. All right, so I'm going to tell you a fairy tale, and then I'm going to back that fairy tale up with computer simulations because every fairy tale is more believable if you have good graphics to go with it. Disney has taught us nothing if not that. All right, so how do we set the peak of the IMF? Well, all right, here's my cloud. This is my theorist's cloud. And I'll just characterize it by the pressure in this cloud. It's a mass to radius relation, and pressure is just a convenient way of quantifying that. Here's a star forming in the center. And let's think about what this does to the temperature distribution around it. All right, now this star starts accreting and sending out light, and I should note that it's accretion luminosity that dominates for these things. It's not nuclear burning luminosity. These things don't, in fact, start nuclear burning until long after star formation is over. It's just accretion luminosity. All right, and I can calculate the temperature distribution around it, and this is the formula. Depends on the luminosity and the density and mass of this blob. And the luminosity, in turn, depends on, well, the accretion rate, which depends on the density and the mass, and this is basically the escape speed from the stellar surface. All right, not surprisingly, the higher the escape speed from the stellar surface, the larger the luminosity. All right, so I can calculate the temperature distribution around this thing. Now I'm going to calculate, well, what's the characteristic fragment mass, the Bonner-Ebert mass? That's basically the gene's mass, but we like it better in the star formation community for reasons that have to do more with sociology than anything else. That's the characteristic fragment mass. Now, let's think about how this varies as a function of distance. Near this star, the temperature is high, and the Bonner-Ebert mass is high. All right, so if I draw a little circle around that star, within that circle there's not a lot of mass, and the temperature is very high. So the Bonner-Ebert mass is much more than the mass around that star. That is, within, say, 10 AU of that star, the temperature is so high and there's so little matter that there's just not enough mass that I could make another star. Even if I took all of that mass and I tried to concentrate it into another star, it wouldn't collapse because it would be too hot. So I can't make another star. As I go away, and I draw larger and larger circles, well, the enclosed mass rises, and the temperature drops, and it becomes possible to fragment. So I'm going to do something really dumb. I'm just going to say, at what distance from this star does the temperature drop low enough and the enclosed mass rise high enough that it would become possible to make another star? And then I'm going to say, the stuff within that circle goes on to the first star, and the other stuff is allowed to make other stars. Now, what's nice about this is that I can actually solve the system of equations and calculate at what mass that occurs. And it winds up depending on two things. One is this escape speed from the stellar surface, and I'll talk about that in a moment. And the other is, in fact, almost everything cancels out in these equations except the pressure. Here's the answer. All right, so here's my characteristic stellar mass. It depends on the pressure and almost nothing else. All right, now let me explain the final step in this, which is I need to know the escape speed from the stellar surface, from this accreting protostar. Where does that come from? How did I get that? The answer is, it turns out, it's a universal constant of nature determined by the physics of deuterium. All right, this is where we get into this technical star formation stuff. All right, protostars have a main sequence. All right, the main sequence that you're all used to thinking about comes from hydrogen burning. All right, and that sets the mass-radius relation of stars. Well, there's a fuel in stars that will ignite before hydrogen does at a lower temperature, and that fuel is deuterium. All right, the ISM is about 1 part in 10 to the 5 deuterium, and that deuterium will burn at about 1,000,000 Kelvin. And that 1,000,000 Kelvin can in fact be calculated from fundamental principles. During the time the star is accreting, it's actually on a deuterium main sequence. All right, so here's how this argument works. Deuterium burning keeps the core temperature of the star at about 10 to the 6 Kelvin. All right, and again, you can get that from first principles. Now, here's where I ask you to all dredge up and remember your polytropes from your stellar structure class. For a polytrope, if I tell you the core temperature, that's equivalent to telling you the escape speed. If you know the core temperature of a polytrope, you know its escape speed. So that gives me the escape speed that I need. And the end result is that I get a characteristic stellar mass that's about right, and that depends on, all right, this is a dimensionless number that has to do with the physics of deuterium. That's the fine structure constant. That's the gravitational fine structure constant. That's the pressure in units of the Planck pressure. So the characteristic stellar mass depends on the pressure, the interstellar pressure, and nothing else, and it does so to a ridiculously low power, minus 1/18. And believe me, I tried damn hard to make that minus 1/18 go away, and I couldn't. All right. So the first order depends on the interstellar pressure and nothing else. That's my fairy tale for why the IMF is essentially universal. So let's check this story. Now, one part. Let me hold off on that question because you'll see in like 3 or 4 slides. All right, so should you buy any of this? All right, well, let's first check. So notice that this story I told you didn't involve the metallicity at all. Now, I'll bring back metallicity at the end. Metallicity actually, when you do this numerically rather than approximately, analytically, metallicity does enter very weakly. But it should be very weak. So does this work? Andrew Myers, who's a graduate student at Berkeley and spent a summer here working with me, did some simulations where we started with clouds with identical initial conditions and just varied the metallicity and did the radiation hydrodynamic simulation and saw, did the fragmentation change? So here's solar, 20% of solar, 5% of solar. All right, this is the long view of density. This is a zoom in on density, and this is the temperature distribution. And from each of these simulations, you can look at the mass spectrum of the stars that formed. You do a KS test, you find there's no difference. So metallicity to first order doesn't matter. Again, we'll come back. It probably matters at the very small level, but these simulations aren't sensitive enough to detect that. All right, let's do the next dumbest thing. Let's take a 1,000 solar mass blob of gas, roughly the size of the Orion Nebula cluster, isolated, no protostellar outflows or anything fancy like that, and let it collapse. All right, here's where the cool graphics come in. Left side is showing you column density, right side is showing you temperature. You'll see the stars start forming, the gas starts heating up. This is a radiation hydrodynamic simulation, so I'm following the radiative transfer through the dusty gas. And it collapsed. Did I get something that looks like the right IMF? Not even close. Totally wrong. But we learned from failure. This is showing the characteristic mass in the simulation as a function of time. And you'll notice that it just keeps on growing. It should be flat, and it should stop at that line. And if you could give me a good reason to stop the simulation right there, that would be awesome. But there really isn't one. So I can illustrate it with this movie. So the green line is the cumulative mass distribution in the simulation, and the gray region is the cumulative mass distribution I should get if I'm following the observed IMF of the Milky Way. So that green line should stay within that gray region. And I'm showing it to you early in the simulation, and I'll show you a movie of how both move as the simulation changes. The gray region is going to change because even though the underlying distribution is the same, I'm drawing more and more stars from it, and so the 10th and 90th percentiles move. All right, the green line should stay within the gray, and it sort of goes, and it keeps on going. So we have to learn from our failures. Why did this fail? Well, it failed because that cute story I told you failed. That cute story where I had my little stars that were islands of warm gas surrounded by a sea of cold gas. In this simulation, that didn't happen. Here's the temperature distribution early in the simulation. You see the gas is mostly cold, but later on, the entire simulation volume has been heated to more like 30 or 40 Kelvin. And that's wrong. Real molecular clouds don't look like that. And the reason is the star formation rate was way too fast. I basically turned the entire cloud into stars in one free fall time. Whereas observationally, it should be more like 1% of the mass per free fall time. So let's try and fix that. Here's another simulation where I now embed my cloud in a larger turbulent volume, and I include the fact that protostars have outflows. Same sort of movie. So you see the gas warming up. All right, but I turn much less of the mass into stars in this one. It's a lot closer to reality. The red line is the new simulation, and you see now my IMF is constant with time, not growing, and it matches the observations pretty well. All right, again, a movie, watch the red line versus the gray line. The red stays within the gray pretty much, which is what it's supposed to do. All right, so I seem to have a way of explaining the IMF from non-isothermal turbulent fragmentation. All right, and the reason this worked is that my gas in this simulation actually stayed cold. All right, so implications, that's what I want to end on. So what does the IMF depend on? All right, well, in the analytic model, in the fairy tale I told you, almost nothing. So all these different colored lines are all the parameters that I tried to vary. All right, so I tried varying the density profile. I tried varying the properties of the protostars. I tried varying the properties of the dust. That's what these two betas are. All right, everything basically makes no difference. Now, what does make a difference? Well, first of all, there's the interstellar pressure. It makes a weak difference. That's, this is a 6.5 decade range in pressure. All right, and I'm getting like factor of less than 10 variation in the IMF for a 6 decade range in pressure. But at high pressures, I do get somewhat lower characteristic masses. The other thing that matters a little bit is metallicity. So these two green lines, those are the ones that vary the most, all right, are for metallicities of 1/10 solar and 1/100th of solar, and it makes a factor of a few level difference. All right, now, this is for the analytic model, not for simulations. The simulations that I showed you before weren't sensitive enough to detect this. I'm doing follow-up simulations that should be. All right, but you'll notice that high metallicity and high pressure combined give you the lowest possible stellar mass. Now, what environments do we know of where the pressure is really high and the metallicity is high? Well, the things that are today the cores of giant ellipticals, probably the highest pressure star-forming environments in the universe, because pressure is basically a proxy for surface density, or it's equivalent to surface density. And I don't know of any regions that are higher surface density than the centers of giant ellipticals, and of course they're metal rich too. All right, so this is at least consistent with what seems to be coming out about the IMF and ellipticals. I won't claim it's a full theory of the IMF yet, but it's actually a physically motivated model that can explain what you're observing. All right, so I'm going to summarize. The IMF is set by the thermodynamics of fragmenting gas, and for the reasons I've argued, this has to be on small scales, not on galaxy scales. I don't think you can derive the IMF from something that takes place on a kiloparsec size scale. You have to derive it from something that takes place on the size scales actually relevant in star-forming regions, which are way below the resolution that any of you people like to think about. All right. The fundamental physics that's responsible for this is the fact that stars accrete and radiate and heat up the gas around them, and that limits the fragmentation. Fragmentation is a self-limiting process. As stars start forming, they heat the gas around them. That heating suppresses further fragmentation. All right? When you make a story that involves that, what you find is that the IMF is nearly but not totally universal, and the two things that it depends on are the interstellar pressure, all right, or equivalently the surface density or something like that, density and velocity dispersion, and to a lesser extent, metallicity. That's the analytic story, and I am now running simulations where I form stars in environments that range from wimpy Taurus in the Milky Way to something like the center of a giant elliptical. I'll tell you what we get when the simulations are done running, which will hopefully be some time before I retire at the rate they're currently making progress. I'll end there.